Hello there. Welcome to a really interesting and expansive problem session. Might take a quite a long time to go over all of the details. Some of that I'll leave it for you to do. So the question is like, if we have an AC circuit with one source, okay, so source is here, and it can be connected in to many different configurations, and you might even have a resistor here, inductor here. You can have a complicated circuit. Okay, so this is a gonna circuit that gonna illustrate that technique, but you can use that technique to solve any AC circuit problem. Okay, so what is the technique? Okay, so the technique is actually take this circuit and convert into what we already know. So if I gave you a kind of, this is the old problem. So if I give you a DC voltage, okay, some V, and I give you a complicated circuit here, a complicated circuit, resistive circuit, just resistance. I expect you to solve that problem by now. Okay, so if you can solve that problem, then you can do that problem by converting this problem into that kind of problem. So this problem, our technique will be learn how to convert this into some kind of resistance. It's kind of, we have a capacitor, we're gonna just we will replace with a something which acts like a resistance, and this one will replace with something which acts like the resistance. And so these are all, you can think of these guys as resistances. So this is like a resistor 1, resistor 1, resistor 2, resistor 1, resistor 2, there's 3, resistor 4. So there's a 4 resistor circuit. And there are many ways to go from finding all the I here, and the I2 and the I1. So there are many ways to find there. And because I is going through this, we can, product of this is the power at any time. Power here is just I times V, and then average power is just time average of this, right? So that's the technique we're gonna learn. All right, it's a very powerful technique, but there is a little bit of math that you have to introduce, and the math is converting this problem. So this problem to that problem involves using complex numbers. So like ZC will become 1 over I omega C. ZL will be I omega L. And why that is the case? Well, we are going to replace the cosine omega t. We're going to replace this by e to the power I omega t. I, is minus 1. And in the end, we're going to so we have kind of introduced something that's this is real and complex. If you look at this complex thing, this actually is cosine omega t plus, so there's a real part and sine omega t. So this is the real part of this guy, and this is the imaginary part. They're also real, this is also real. The imaginary part, because it's multiplying I. So to go back, so all the answers will be what we're going to obtain by doing this. We're going to obtain these I's. These I's we're going to obtain will be actually a complex kind of thing, will be complex. So I will be some kind of real I plus I times some kind of imaginary I. And so actual current will be this. So we will do algebra to get that out, okay? So we can go a little bit of complex analysis we are going to learn. That's sufficient to kind of address this problem. All right, so maybe you're ready to learn some complex analysis, beginning of complex analysis. And this is exciting because, you know, algebra, whenever you have to do trig things, multiplication of trigs and addition of trigs and all kinds of things that you have to do involving trigs, using exponential, this identity that this equals that makes algebra in terms of this kind of things, and that turns out to be much easier to handle. You get the same answer because these are linear operations. You get the same answer as long as you're in the linear domain. It's the same answer. Just read off the real part. So the things that don't go over and have to be very careful when you're thinking in terms of power and energy. Because when power, you have multiplied I and V. Now it's not linear anymore. And then you have to be very careful. So in here, when you're dealing with a complex, the power will be I star V. And so this will be, what is star? Star is replace I by minus I. Okay, so I would kind of stop here and clean up this place and introduce just a little bit of complex, how to deal with complex, and then we can just look at the origins of these two formulas and how they actually end up in the equation. All right. Before we get on there's just a notation, because some of you may not remember, omega is angular frequency, which stands for 2 pi f. F is the real frequency. So like a common household in the United States, it operates at 60 hertz. I believe it may be 50 hertz some places, but here it is 60 hertz. Means hertz is a cycles per second. So this is oscillating 60 times per second, 60 cycles per second. So that we'll call it 60 hertz. Hertz stands for cycles per second. Okay, we're not going to use numerical things. We're just going to stay with the conceptual things. All right. So what is a complex number? It's actually any number that has a square root of -1. We'll call it complex number. So we can use a symbol for it, a symbol for usually I in physics, and J by, electrical engineers. I don't know why they do that, but in electrical engineering books you have J for this. In math books and physics books you have I. Okay. Now, for instance, I've got a 3 plus I times 4. You can also write 3 plus 4 times I. It's the same thing. You just think this 4 is somehow different than this 3. That's what we're saying. So 4 is different than 3. So sometimes you can visualize this in a diagram. You can say, whatever, not multiplying I, this number, I'm going to do like X, along the X grid. So this is that point this is 3. And what's what this number that multiplies I'm going to plot along the y-axis. So I'm going to use the same scale for these two. So this over here, 4. So 4 is over here, 3 is over here. So 4 is over here, and so this is the point. So this is that represents that guy, and this represents that guy. So this represents this number, which if we call it say A, so that represents point A, that value A, that point represents value A, and A is a complex number. You can see 3 is we call it 3 is the real part of A, and 4 is called imaginary part of A. So I is not part of this definition. You just say this is the guy which goes with I. Okay, and if you had I also, then I couldn't really plot this, right? So these are real numbers, and this is also a real number, but this guy is representing two numbers. This represents 0.34. So 3 is the real part of the number and 4 is the imaginary part of the number. So to get the number, I have to take 3. So the A itself is 3 plus I times 4. I like I times 4. Some people like 4I, but I prefer that way. It helps me keep track of things. So you can see that this is 0, 0 from, so there is a vector notation which is called phasors for these things. So this is a notation. You can say, oh, this arrow represents the same thing as that. So there is no vector here, but I can just think. This is very common to think. And so this distance will be just a square root of 3 square plus 4 square, which happens to be 5. And this will be arctangent of 4 over 3. So that will be the angle. So this is usually represents R and this represents theta. So this various representations of that. When you add, say, the B, which is like a 1 plus I 5. So when we add A plus B, there's going to be a real part of this imaginary part to that. And you can see over there, I have a 1 and 5. So it's that point. So this B is that point. And if I add these two guys, so I will add 1 to that, 1 to this to go this side, and 5 over here to that. And so I will end up, so this is the B vector, this is the B vector, this is the B vector. And so the sum will be this vector. So you can see the vectors is a very nice way to thinking about it. So this is the sum. So the C is the sum, and the real part of this plus real part of that. So 3 plus 1, that gives the real part, and then this is 4 plus 5. So we got this number is 4 plus I 9. How about multiplying? If I multiply A with B, multiply it. Usually you write nothing, you just write A, B, and just like regular math, you understand that this is actually multiplication. So when you're multiplying this, let's call it D. When you multiply, you just get just regular multiplication. So 1 plus I 5. So we distribute it. 3 plus I 15 plus I 4 plus I square 20. But I square, if you do I square, is a minus 1. See, right? I square is minus 1. So this becomes minus 1. So this will just becomes addition of two numbers problem. So that's just a minus 17 plus I 19. How about divide? Say g equals to a divide b. Now that's a pretty hard problem. So I just have to write down 3 plus I4 and 1 plus I5, and I'm stuck now. So the trick is to convert the denominator in a real number. So how do I convert, what do I do to convert denominator into real numbers? So if I have some x plus iy, and I wanted these guys to come out same, so those were the cross those are the cross product, like imaginary part multiplying that, and this guy was multiplying that, right? So those are those guys, which means if I multiply this number with x minus iy, then this will become a real number. This will simply be x square plus y square. Okay, you can check. So what I can do, I play a trick to convert denominator into a real number. Just multiply by, and so the denominator becomes a real number, and the numerator just a multiplication to complex numbers. So just like that, so this will just turn into, you know, some x plus iy, and then the denominator will be some number n. It's real numbers, and so this is going to be x over n plus iy over n, and so this is another number. This is the real part, and this is the imaginary part of this number g. So that's one way to multiply it. Okay. All right. Let me quickly do another representation of it. So let's go. When we did this, put a number. Say this was a, and this was b. Let's call this x, and this is y. X direction, this is y direction, and this was some number z. We can call it x plus iy, or this point is x comma y. So we said we could represent this by this r and theta. So the r will be square root of x square plus y square. You can see r square is x square plus y square. Well, this same as this is equal to x plus iy times x minus iy. So when we do this, we just use a trick, but it's a very good trick. So if we call this number z, then we call this number a complex conjugate of z, called complex conjugate, and usually put a star over there. Complex conjugate of g. So if this is a number z, complex number z, and then this is a complex number z star, just I goes into minus I, and we multiply them together, then you are going to get the square of the distance from the origin in such a plot. So this is called rectangular rep, x plus iy, for this number z. Now you could say I could represent something like this, just give you the distance r and theta, so the r will come out like this. So r will be square root of z star, and theta will be arctangent. So this right angle triangle, you can just do y over x. But you have to be careful. You can see that this, if I go this theta and then I add 2 pi to it, I come back to the same point. So you got to be careful, and so theta goes from 0 less than 2 pi. So we just cover just once around. That's it. We don't keep going over and over again. You will learn later some things like if I had functions of complex numbers. So if I had a z and there was some function, say function of x is a square root of x. So that you already know. But so if what is f of some complex number z, which is square root of z x plus iy, what is that? How do I get it to become a mapping? So for x, you know, if I have this is x, so take say 4, and this function maps it to 2. So we have this rule, this point goes to that point. And so over here is a z, which stands for x plus iy. Okay, now if I do square root of 2, where do I go? I go this point, that point, where do I go? So this mapping will have to tell me what, it will have to tell me a plus ib. So what are the a and b I can go? It's very interesting and it's taking me away from my main thrust to the point, but this actually is not an easy question to answer, and you might want to look up some other book. Okay, so I am here now, so I can represent this number x plus iy by rectangular way or polar way, r theta, and this is called polar representation. So if you do e to the power, say I some real number, say x, okay, so this is real, and so this you can show that this is equal to cosine theta, cosine x plus I sine x. And there's many proofs of this. There are a couple of really interesting proofs of this. One is just expand and collect terms. So if you expand in Taylor series, so you're going to get 1 plus ix plus ix square over 2 factorial plus ix cube over 3 factorial, and so on and so forth. You can see that this is will have this is the real part, this will have real, all the even terms, these guys will all end up becoming cosine, and all this odd terms will have I of x, and it's also have I of x. So all these terms, this will become sine x. You can show that, but this is Euler's formula, and this is the most important formula you should remember. So any number, this is a real number, but because this whole thing is complex, so this is a function which is equivalent to this expression. So usually we have e to the power I theta, that's going to be cosine theta plus I sine theta. Okay, now I'm going to use e to the power I theta to cosine theta plus r I sine theta to kind of relate these two guys. So I say r, let's look at e to I theta. So this and this, using that, look at this combination. What is that combination? You have a r, and it's going to be cosine theta plus I sine theta, and now we'll expand this, r cosine theta plus I times r sine theta. But if you look at this triangle, this is x, and that's r cosine theta, and this part is y, and this y is r sine theta. This is equal to x. So you have this is x, and this is y. So this is x I y, but this is the same as the z. So this representation of z is actually same as r e to the power I theta, as long as we stay in this. So okay, so that's a very really interesting point, and we're going to use all of this now in here. Okay, let's now got the basics. Now we can try to solve this this problem. of this circuit. Okay, so here, you know, if you voltage drop across a capacitor, you can see if I take if the current in a capacitor, well, let's look at resistor first. When a current I is going through resistor, the voltage drop across here, so the voltage drop across resistor is equal to just IR, and so they are between this and this we can this is resistance, and we can call it what is impedance of a resistance. For the capacitor, if I ask the same question, I'm going to have 1 over C if the current I is going through it. So I need to do this integral, and then there's going to be voltage across the capacitor. So voltage across the capacitor. Well, if this is varying as e to the power I omega t, so this will vary as e to the I omega t. So you can say 1 over C, something for varying as e to the power I omega t, t prime, dt prime. This can be complex, but as long as const doesn't depend on time, this is time independent part, then I can pull this out, and there's going to be I0 over C, and then I have I omega e to the power I omega t, and that's the voltage capacitance. So this is if you look at IR, and so the voltage is also going to go as some V0 e to the power I omega t, VC V0C is I omega t. So, and you can see already I omega t will cancel out, and then if I think about this, then this part here acts like a resistor, and we call it this is the impedance of the capacitor, or capacitative impedance. So I use the letter Z and 1 over I omega C. Now you can see that in parallel circuits, one of a resistance adds, right? If the circuit, if you have a resistor R1, another resistor R2, and they're parallel. So if there was a resistor R1 and this R2, they were parallel, then what adds is 1 over R is 1 over R1 plus R2. You remember from before, right? So the inverse adds, and inverse of this is called resistance, right? And so 1 over inverse is called, do you remember that? This is called conductance. So there is also a word of 1 over ZC will be admittance of capacitor. Okay, so this is some words. This is a complex thing, so in the analysis there will be complex thing coming in. So now if I do same thing for the this inductor, and the current I is going through, so what's the voltage drop? And this is going to be L di dt equals to V. So if this is this will be also some complex number, but I will go as time part will be just like that. So this L some I0 e to the power I omega t times I omega, and on the other side will be some V0 e to the power I omega t, V0L, and so I omega t will just cancel out, and you can see that I omega L is acting like a resistor, and so this is where we call it impedance of this inductor, or complex impedance of inductor. And both of them are kind of same kind of deal, right? Of course, the admittance of the inductor will be 1 over I omega L. So you can see that as the omega goes very high, this will become small, right? For a large frequency, the resistance, this resistance will kind of dominate. At a smaller frequency, this resistance will dominate, this net will dominate. And so you can actually simplify circuit depending on the frequency and the values of C's, even before you start to muscle through the circuit. Okay, but we're gonna just do muscle through the circuit. Okay, let's try to write the equations of this circuit, and let me put some names here, C and D. And first step is to convert this into inductances, you know. So we have we write just box 1 over I omega C, and this is I omega L, R1, R2. Oh, this was R2, and this is I omega L. I wasn't looking. So this is A and this is B. Let's call this C, D. So now I can just pretend I'm in a DC circuit, and this is going to be V0 e to the power I omega t. I just pretend now. Everything is complex. This I is complex. This I is complex. This I is. These are all real, and this I's are complex because V is complex, and there is everything is complex now. So we have to just kind of set it up, just like. But I'm going to pretend and just going to set it up. So first notice that I1 is equal to I1 plus I2. So this, the current comes in, divides, and it has to be the same because over here no current is accumulating. Then we can do the loop equations. So you can do V0 e to the power I omega t must be equal to the, you know, the drops from here is minus I1 over I omega c minus I1 R1. So this, I just got the I1 right away, right? So this is minus I1 R1 plus minus I over omega c. So what I did in one step, I kind of converted this. So very nice thing, 1 over I is actually minus I. How do I know that? Well, I can just 1 over I can just multiply I with I, and because I want to convert this into a real, so I have to do this to make it real. And so this is I over minus 1, and so that's equal to that. It's very easy to see that. Okay, so the I1 will be easy. So I'm going to write you need a 3 equation, right? So another one will just go all the way that second branch, and so second branch is V0 e to the power I omega t and equals to minus I2 R2 minus I2 times I omega L. So I get I1 from here, I2 from here, and I from there. So I get all of these guys. So I get I1 equals to V0 e to the power I omega t, but I need to figure out the real part from here, right? And so we should sometimes people write like, oh, this have a notation like that, just distinguish the two I's. And so these are all tildes, you know, too much writing, but if you don't get confused, then you can learn this in the context. So this is a minus, so going to be minus, and then R1 minus I over omega c. So it's gonna pretty complex. So I need to be able to write as some kind of real part plus I times imaginary part. I need to convert this into that with the tricks we just learned, right? And we're going to do something pretty soon. I know that I'm taking a lot of time, but this is kind of time worth spending, because if you're a student who is kind of likes a little bit hard stuff, this is going to be very enjoyable to you. So this one is going to be the same way, minus v0 e to the power I omega t, and instead of this way, it's going to be just r2 plus I omega L. Okay, and that will means I will just be this plus this. I tilde will be just I1 tilde plus I2 tilde. So I need to figure out its real part 1, real part 1, right, and real part 2, imaginary part 2. So this will be just the sum of these guys will be the real part plus I imaginary part. Okay, I'm going to try to clean up and do this, trying to figure out how the real part of this going to look like, what this I1 tilde looks like and I2 tilde looks like. Okay, and I'm not going to try to do it real part. I'm going to do it this way, and also I'm going to write it as some I10 exponential I and some angle phi 1. So this will be like the other version. So this way of writing is a rectangular version, and this will be polar version of the same complex expression, that, right? So let's try to do. Okay, I got clean board now. So I want to do this. You can see this top part is kind of like a complex number in a polar form, but except this negative part here, which I can absorb into the numerator over there. Say minus 1 is actually e to the power I pi. So if I have a minus e to the power I omega t, so it's going to be e to the I pi times e to the I omega t. How do I know that's the case? That's a cosine pi plus I sine pi, and this will go to 0. So like minus 1 can be written in a complex way. In this is a very nice way. It's actually one of the most beautiful equations. E to the I pi, e to the I pi equals minus 1. Good to remember. And which of course equal to I square, you know. So this is so you can write this guy that will simply be v0 e to the power I omega t plus pi, like that, because numerator will add because you have e on both. E is the regular e. Okay, so we can write this is v0 e to the power I omega t plus pi. I hope I didn't make a negative sign error. Sometimes I make negative sign errors and it's going to be trouble. So denominator is r1 minus I over omega c. Now it's like I can proceed in a couple of ways. One is to write this guy. If I were to write this guy is some r e to the I theta. Suppose I convert like this. So then this will go into v0 over that r e to the power I omega t minus theta plus pi. And so real part of this, so this will go into v0 over r cosine omega t minus theta plus pi plus, so this is the real part, plus I times v0 over r sine omega t minus theta plus pi. Okay, and this is the imaginary part, and this is the real part. Okay, So we see the steps in the future. So it depends on just converting this guy like that, and that's my preferred way. That's let's do this out, and then, but there's another way of doing it. So I can get all the way there just by knowing what r and theta are. It's very easy to get r from here. So this r will be, this is a plus, it's kind of like a plus ib. So this, think of this as x plus iy. Y is this and x is that. Okay, so this r is square root of r1 square plus minus 1 over omega c square. I didn't need to write minus there because I'm going to square it anyway. And theta will be arctangent inverse minus 1 over omega c divided by r1. So this is simply arctangent inverse. This minus comes out, and this is 1 over r1 c times omega. So that kind of solves this whole thing. We already got all the answer. You can put, they look messy, but we have the answer. So we have I1. So I1 tilde, I1 tilde is this stuff. Let's call this A and let's call this B. So I have A, let's call it A1 and B1. So you have A1 plus IB1, and you can do the same thing, and you are going to get omega L for this. And so wherever you say 1 over omega c, you get minus 1 over omega c, this will be just, for R2 it's just going to be, for I2 this is going to be omega L. And I want you to carry it out, okay? So I2 tilde will be A2 plus IB2, and so I tilde will be A1 plus A2 plus IB1 plus B2. So you can see I've got this guy, this guy, this guy. So power of the source I can get from I tilde. So I tilde star V, V as in V e to the power I omega t. So there is a, yeah. So when you're using that, you can use just this part when using it in here instead of rectangular part. So this is the polar part. So you use that, you can, this I omega t and this minus I omega t will cancel each other, and there's going to just be a particular expression. Okay, so this is going to be just a this is going to be so let me write that down for power. So you have I tilde will be V0 over, let's call this R1 for in here, and the other guy will have R2, V0 over R1 e to the power I omega t minus theta 1 plus pi, and the other one will be V0 over R2 e to the power I omega t minus theta 2 plus pi, and V will be V0 e to the power I omega t. So when I multiply this with the star given here, I think it's there is a factor of half here. When you average the power, you're going to get a factor of half here. So half, this becomes minus and this is plus, they will cancel each other. So you're going to get V0 you're going to get V0 square. V0 will multiply all of them, R1 e to the power I minus theta 1 plus pi, this minus this, plus v0 square over r2, it's a minus I minus theta theta 2 plus pi. So the complex power will be obtained using this, you know. Okay, so it's a real part of this will give you the real average power. All right, let me move to get VA minus VB. That's a very interesting part to me. Okay, so I hope you followed that. I'm writing I1 tilde is just A1 plus IB1, and I2 tilde is A2 plus IB2, and I tilde is just A1 plus A2 plus IB1 plus B2. And I'm going to try to now do something to show VA minus VB. So if I'm thinking of this as a box and this is a box, then it's kind of like if I know voltage here, then what's the voltage drop across here? That's the VA, right? So you probably know this voltage is simply the voltage of this guy here. So VC is just the V0. So what's the voltage? I1 times ZC. That's the voltage across here. That should be equal to voltage at point C minus voltage at point A. And if I do I2, this is tilde. So and this is the tilde, and I2 tilde, and this just R2 is equal to VC tilde minus VB tilde. So if I want to know the difference, I just subtract the first one from the second one. So this will give me on the right side, I'm going to get a VA tilde, but take a minus 1 times this and add it. Okay, so that's just good. And this one give me minus VB tilde. So I'm getting a complex potential difference between the two, and so I'm gonna get a I2 tilde R2 minus I1 tilde GC. So to answer this question, all I have to do is find the real part of it. So VA minus VB is just the real part of VA tilde minus VB tilde. Okay, and I will try to do this based on, suppose I've already done that and I've written down on a piece of paper what A1, A2 and B1, B2 are. And so I don't want to write very complex one. I want you to appreciate the process by which you can actually handle pretty much every problem. All right. So the thing is to do this guy. So I'm trying to get I2 tilde R2 minus I1 tilde GC. And I want to get written down as A plus IB. So I want to convert that into some number A plus I times some number. So these are real parts. And then I will read up this number. That's the answer. So I2 tilde is already A1 R2 plus I B1 R2. This guy is I2 is, these are 2's, and this one is just A1 plus I B1, right? And this, but GC is 1 minus I over omega C. So this actually, which is real and imaginary, just kind of switch when I multiply this out. So this remains the same, so this is same, and so this one is actually minus minus plus I a1 over omega c, and this is this minus this becomes plus, and this I with this becomes I square, and this becomes a minus b1 over omega c. So this guy will go with that. So this a, so if this was some a plus ib, then this a is just this part plus that part. So this is a2 r2 plus actually minus b1 over omega c, and b is b2 r2 plus a1 over omega c. So the answer for VA minus VB is just this stuff, a2 r2 minus b1 over omega c. You can see that these will be 0 if this equal to 0, right? So if you wanted to find out, more of this, the full expressions of this, go through the calculations and fill in all these details. It's very instructive. You could practice with that. Probably do it with another friend so you can check with your answers. And so sometimes people ask, when would difference will be 0? So if I were to kind of attach a voltmeter across this and try to measure the voltage, when will be the 0? When 0? So that question can be answered when this equal to, you can see omega times RC has to be equal to R2C has to be equal to B1 over A2. So you got to figure out these guys, and then you can get the condition when that that depends on the impedance. When you work it out, you'll find out that depends on the impedance. So it's a long winded calculation. So the only thing remaining is, suppose what is equivalent impedance? Is equivalent impedance is the same thing as equivalent, if I were to kind of replace all of this by simply one box with Z. So this will be exactly same as the resistance. So these are those back boxes. So we want to replace this with one box. Okay. Well, how do I convert this? So this is going to be converted into, you've done before this kind of stuff with resistors. So it's going to be like this, and then you're going to go into that. So this is ZC, R1, and R2, and ZL. So this is going to be R2 plus ZL, and this is going to be ZC plus R1. Now these are in parallel, so you're going to have an impedance of this. So this is going to be equal to 1 over ZC plus R1 plus 1 over ZL plus R2 inverse. So this will be the Z equivalent. So Z equivalent will be like that. So there are many other questions you can answer once you map it into kind of like a semi-resistive circuit. It's not resistive because there's a phases involved here. And this is a very long video, and this is the last video on AC circuits I'm going to do. I will go back, and next I'm going to do the transformers, coupled circuits. When the two circuits are coupled like in transformer, you have one circuit, another circuit, but then inductance kind of couples the two circuits. And once you set that equation up, it turns out to be similar to the doing of the AC circuit, and that's why I did the AC circuit first. And coupled circuits are very important in experiments. Lots of experiments are in physics are involve coupled circuits, and it's important to learn how to separate them, how to find the modes, etc. So we can talk about that in another video. So if you like it, please hit a like button. If you haven't subscribed, appreciate if you subscribe to this channel. You can check out more of my physics writing in this website. Take care and bye.